A very good evening, good afternoon, and good morning to all. I, Dr. Pallavi Saxena, SSC member of iLEAPS, and Dr. Gary Heyman, Project Administrator iLEAPS, welcomes you all on the occasion of our 7th talk in iLEAPS Global Colloquium series. So let's have a short introduction about iLEAPS. So iLEAPS is Integrated Land and Atmosphere Interactions, which is a global research project of future Earth. iLEAPS provide understanding of how interacting physical, chemical, and biological processes transport and transform energy and matter through the land-atmosphere interface. The prime purpose of this colloquium is to introduce a scientific society people with the distinguished and significant work of eminent scientists all over the world. And it is a very bright opportunity, particularly for the early career researchers, to interact with the distinguished speakers and establish the bridge between the ideas and knowledge through this platform. So our today's speaker is Dr. Roy M. Harrison, who is Queen Elizabeth II Birmingham Sanitary Professor of Environmental Health, University of Birmingham, UK, and also Distinguished Adjunct Professor of King Abdulaziz University, Saudi Arabia. His research interests are in air pollution, especially airborne particulate matter. He has also been heavily engaged at the science or policy interface as a member of several government technical advisory groups for the DEFRA in the UK, including past membership of DEFRA's Science Advisory Council. He was a contributor to the World Health Organization Global Air Quality Guidelines and the Guidelines for Quality of Indoor Air. He was appointed an officer of the Order of the British Empire in 2004 New Year Honours List and elected a Fellow of the Royal Society in 2017. He is the author of over 600 papers in the peer-reviewed literature and is listed by Web of Science as a highly cited researcher. So today he will be talking about future trends in air quality and potential effects on climate change policies upon local air quality, where he will discuss about the various types of gases, that is particularly NOx emissions, and how they and the zero carbon emissions, how they will benefit both climate and air quality, and what are their role in maintaining the climate change policies. So now I will hand over to Professor Roy. And Professor Roy, now the floor is yours.
Well, thank you very much, Pallavi. I will attempt to share screen because I've only seen my screen so far. So tell me can you see my screen now?
Yes,
yes we can.
Yes.
And it seems to be in presentation mode, Roy.
Well, thank you very much, Pallavi, for that introduction and for the invitation to speak to the iLEAPS program, and to Gary for putting the arrangements in place. My screen has now flashed to a picture of you, Gary, so I don't know whether the others who are watching can see my slides or see you.
Roy, I can see your slide, so if you'd like to proceed. I'll turn my camera off and just see.
Well, I have oh, good, my slides come back again. Right, thank you. Now, I'd like to start off by saying something about future trends in air quality, and then I'll go on to talk about climate change policies and how that may affect things. Now, since you're probably quite a broad audience, I will just give one slide which will be totally obvious to most of you, but just in case it's not to everybody. And that is to make the distinction between globally acting air pollutants like carbon dioxide, methane, and nitrous oxide, which are greenhouse gases, and locally acting pollutants, which are those things such as PM2.5 and nitrogen dioxide. with effects on health. And unfortunately, policy tends not to look at the two in a connected way. And indeed, we even have separate government departments looking at them in the UK who perhaps need to speak to one another more often. So I will be asking later on how net zero policies that are essentially addressing the greenhouse gases affect local air quality. But first of all, a little bit about the trends or the drivers of local air quality. And what we are beginning to see in the Western world is the impact of catalytic converters and the move over now to battery electric vehicles. Now, catalytic converters over the past probably 10 plus years, well, 20 years for improvements in carbon monoxide VOC and to some extent NOx from gasoline vehicles. But in the last 10 years, particle traps on diesels have made a very big difference to primary pollutant emissions from road traffic. And we've had a continuing problem in Europe from NOx from diesels, but that now, because of the change in regulations and increasing use of selective catalytic reduction, is beginning to have real benefits for NOx emissions and nitrogen dioxide concentrations. But the future lies in battery electric vehicles, and most governments have set a deadline by which only battery electric vehicles will be on sale into the light duty vehicle market. But as I said, in the last 10 years, we have seen some real benefits, and there we see reductions in black carbon, which is primarily in the UK an exhaust emission from diesels. And that started in around 2011, which is when the Euro 5 standard came in on new diesel light duty vehicles. And quite soon afterwards, there were new regulations on heavy duty vehicles. And we've seen a really substantial decline in black carbon at roadside since that time. But that didn't bring out on the sort of benefits in nitrogen dioxide that we would have hoped to see. So battery electric vehicles, as I say, very much of the future, and they will eliminate NOx emissions at the point of use and eliminate CO2 emissions if a renewable source of electricity is used. They won't, though, eliminate particulate matter emissions at the point of use, and this has been quite a controversial issue, which I'll go into in a few minutes. So this is results for nitrogen dioxide, looking at 6 different major cities around the world, from London in the top left to Beijing in the bottom right. And the left-hand bar is a measurement from a roadside or an average of a number of roadside stations. The one next to it is the urban background, and the one next to it is the rural average concentration. So these are annual average concentrations taken from major sites within those cities. And what we see is a huge increment in nitrogen dioxide at roadside and a large urban increment. And because battery electric vehicles will not emit nitrogen dioxide at the point of use, we should see a huge improvement in the roadside increment and some improvement in the urban increment, which isn't solely due to road traffic, but road traffic is a major contributor to it. So we do expect to see some major improvement there. But then the problem we have with particles is we have non-exhaust emissions from traffic. So we have brake dust from wear of the disc and pad, tire dust, road abrasion particles, and resuspended road surface dusts. And they're all important contributors to airborne concentrations. And they've become far more prominent. So here for PM2.5, This is from the emissions inventory. These are not concentrations, these are emissions for the United Kingdom. In the yellow, we see the exhaust emissions, which between 2000 on the left and 2020, which we see about 2/3 the way along the date axis there, we've seen a massive reduction in PM2.5 emissions from road traffic, whereas the other colours, which are the brake wear, road abrasion and tyre wear, are still increasing, and since probably around 2016 have exceeded the exhaust emissions. And that's not true only of the United Kingdom. The next graph shows it for the EU 28 countries, or 28 as were, up until the late 2010s. So this is going up to about 2018. And the exhaust emissions are the solid black line that comes from the top left and goes down to the bottom right, and the road abrasion, tyre and brake wear at the bottom there. And by the end of this graph, which is about 2018, they were just taking over as the major part of the road traffic emissions. And that's true also of VOCs from road traffic, where we see a line here for vehicle exhaust. This is the vehicle exhaust line, the VOCs in vehicle exhaust. The evaporative emissions are the line below that. And then the bottom line that's got the triangles and is going upwards slowly is the non-exhaust VOC, which we see here, which now exceeds the sum of the exhaust and evaporative fuel losses. And you may wonder where those VOC are coming from, the non-exhaust ones, and that's mostly screen wash and evaporation of engine coolant. So we really are seeing non-exhaust emissions taking over. So if we look now at PM2.5, again from 6 cities, London on the top left, Beijing bottom right for Beijing. Again, road increment on the left, and then, well, road traffic sites, urban background sites and rural sites, we see the increments. Now for PM2.5, they're not nearly as large at roadside as they are for nitrogen dioxide, but they are still important. And the question is, are we going to see those decline as we move to a battery electric vehicle fleet? So it has been suggested that battery electric vehicles are heavier than their equivalent internal combustion engine vehicle. And a greater vehicle weight implies greater abrasion emissions and dust resuspension. So we might expect to see more emissions than the battery electric vehicles. But against that, a lot of braking on battery electric vehicles is regenerative, and that means just take the foot off the accelerator, and then instead of the engine working as a driver of the vehicle, it acts as a generator. So the inertia of the vehicle drives it round, it generates electricity that recharges the battery, but that has an effect of slowing the vehicle. And the actual effect of the emissions is very much influenced by the extent of regenerative braking. So the net effect overall is uncertain. So with my colleague David Beddoes, we looked at the weight dependence of, in this case, brake wear emissions, but we looked at it for all 4 non-exhaust sources: brake wear, tyre wear, road surface abrasion, and resuspension. And we see here on the graph on the right, we see emission factor on the y-axis and the vehicle weight on the x-axis. And so we have this curvilinear dependence of the emission factor for brake wear on vehicle mass, and we can use that to differentiate between the battery electric vehicle, which we surveyed and found was generally heavier than the internal combustion engine vehicle. And we can see how much that's going to affect the emissions. And we did that for all of the 4 sources. And then when you put that together, here for emissions of PM10 from a gasoline or petrol vehicle, we see for 3 different road types, so the groupings of bars are different roads, urban on the left, rural on the center, and motorways on the right. We see 4 bars. The green bar is the internal combustion petrol engine. Next to that, the dark blue is the battery electric vehicle without regenerative braking. And then with 90% regenerative braking, which we think is probably realistic, and then with 100% braking regenerative, which is unlikely because the friction brakes will be used for rapid braking and emergency stops on essentially everyone's vehicle. But what we see is, in fact, the only real improvement is going to be in the urban area if we look at the 90% regenerative braking. As far as the rural roads and the motorways are concerned, there's very little change. And we did that for both PM2.5 and PM10. So PM2.5 results at the top, PM10 at the bottom, and petrol on the left and diesel on the right. And this is even allowing for the emission of particles from the exhaust of the internal combustion engine. So we allowed for what the emissions inventory tells us the petrol and diesel vehicle emits from the exhaust as well as the non-exhaust sources. And we see that, generally speaking, there are some minor improvements, or in the case of urban driving, more significant improvements, as long as we allow for the 90% regenerative braking. But there won't be a large difference between the battery electric fleet and the petrol and diesel fleet. Now, moving onwards, there are other factors changing the air pollution climate. So as well as traffic sources, there are other non-traffic primary sources. And something that's attracted quite a lot of interest recently, but is not in many emissions inventories, is cookie emissions, which in urban centres can be very important. And also biomass burning. And Europe, unfortunately, is suffering a lot of wildfires at the moment because we're suffering very hot and very dry conditions. And Southern Europe has a lot of wildfires, and they may spread further north. We've got very hot conditions in the United Kingdom at the moment. So wildfires likely become more prevalent, and they are huge sources of particulate matter and small sources of NOx. And domestic wood burning is an issue because it's often perceived as being carbon neutral, and indeed it does offer some benefits relative to fossil fuels in terms of reduced carbon dioxide emissions or net carbon dioxide emissions. But it is a substantial source of particulate matter and a small source of NOx as well. And this bar chart shows emission rates from a 5 kilowatt wood stove at the very bottom, meeting some of the most recent emission standards compared to different kinds of heavy duty and light duty vehicles. And we see if we move up 3 from the bottom, you see the Eco Design Directive stove, which is the latest set of regulations just to have come in. And that's still emitting a good deal more particulate matter than the even the heavy duty, let alone the light duty vehicles. So at the top, we've got the Euro 5/6 diesel passenger car, which is a lot cleaner than your average wood stove. So there are some questions to be addressed there if we want to improve PM2.5 concentrations as to how much we're going to legislate to reduce the emissions from wood stoves or to fit better abatement devices on them. So those are some of the sort of moving features of primary emissions. We've then got a lot of secondary particulate matter, which in many countries dominates over the primary particles. And there are questions about non-linearities. So if we reduce sulfur dioxide emissions by 50%, will we get a linear reduction, a 50% reduction in sulfate or not? That's very much an open question. A lot of the models suggest we won't. And then there's secondary organic aerosol. And it's very hard to predict the trends there because we don't even reliably know all of the sources. And that comes from both anthropogenic VOC oxidation and also biogenic VOC. So there are important implications there for the biogenic emissions. And just to give one example here, the top grey line shows the emissions of NOx in Western Europe between 2000 and 2019, I think, is the last year there. These are the NOx emissions from a group of countries whose emissions affect the United Kingdom. Below that, we've got the NOx concentrations in micrograms per cubic meter, which are reducing at a broadly similar rate. Note the axes are not the same, so we don't expect parallel lines, but actually if we analyze the gradients, the NOx are coming down, the concentrations are falling at about the same rate as the emissions inventory is predicting. And then in the blue, near the bottom, we have the nitrate concentrations at this site in London. And they've changed very little over that period since 2000, and indeed at the very end of the period seem to have gone up again. So we do, particularly in nitrate, see signs of non-linearities, which means that even though we reduce NOx, we're not going to see commensurate reductions in nitrate, which is not good news. Although for nitrate, it's very sensitive to ammonia emissions. And we need to pay attention to the emissions of ammonia. Now, moving on to the question of climate change policy, we very much talk about net zero in the United Kingdom. We're not going to go to zero carbon, but there is policy to go to net zero carbon emissions by the year 2050. And we've also been very much engaged in studying things in China, where the policy is to go to net zero by 2060. And this is the cover of a report which the Royal Society produced in the UK, looking at how net zero policies would impact on local air quality. And it quite nicely sums it up in a diagram where, as we move from the middle upwards, air quality gets better, local air quality. As we move from the middle downwards, air quality declines. As we move to the right, we see a climate change benefit. And as we move to the left, we see a climate change detriment. So there are 4 quadrants here. And I'm going to address, first of all, the top right-hand quadrant, which we see in enlarged, emboldened typeface in green. So electrification of transport and home heating with wind and solar power is a win-win, both for air quality and climate change. Carbon sequestration by planting trees with low biogenic VOC emissions is also a win-win. Improved nitrogen efficiency in agriculture will help to reduce PM 2.5 concentrations, and also will use less energy in producing the nitrogen fertilizer. So that's a win-win. And a modal shift in transport from passenger cars to walking and public transport would be a win-win. If we move to the top left, then reducing sulfur dioxide emissions will very definitely improve local air quality. And some countries very much need to do that. But we're already seeing that it's reducing sulfate aerosol, which tends to reduce global warming. The sulfate reduces global warming by reflecting away incoming solar radiation. So we actually see a climate change detriment, but I don't personally see that as a reason to stop reducing sulfur emissions. It's something we have to do. Bottom right, so this is climate change benefits that cause decline in air quality. If we plant the wrong trees, we'll get high BVOC emissions, and they will lead to formation of ground level ozone and of particulate matter. So we do have to be careful to get the correct trees, and then we can get a win-win, as in the top right. If we reduce ventilation of our homes and offices, we'll get a decline in indoor air quality, although we may see some reduction in energy consumption. And combustion of biomass or of hydrogen could well lead to increased PM 2.5 and NOx, even though they're good for climate change. And then finally, the lose-loses are essentially continuing to do what we do. So continuing increasing global methane and continuing to burn fossil fuels. That's very much a loser's situation. So that summarizes the main findings of that Royal Society report. There are some other features I'd just like to talk about. So reduction of fossil fuel consumption, as we say, is a win-win for global climate and air quality. Now, there's much talk of using hydrogen. If we generate it from electrolysis of water, then that's referred to as green hydrogen. And that's generally very good, but we can also make hydrogen from methane. And that's so-called blue hydrogen. And that's liable to cause methane slip. So loss of methane from the process, and that could be quite a problem, leading to increased ozone, as well as the fact that methane is a greenhouse gas, quite a potent one. Combustion of that hydrogen, if we burn it rather than use it in fuel cells, and to use it in fuel cells, it's got to be very clean. But if we burn it, that's a source of NOx. And that's being discussed for domestic heating in the United Kingdom, but it would remain quite a significant source of NOx. And then ammonia is being suggested as a fuel for shipping. And the loss of ammonia from ammonia slip during storage and use would be a problem for the atmosphere. And if it is burnt rather than used in fuel cells, it will give rise to NOx emissions. So all of these things need considerable care and concern in planning policies. So what will happen to ground level ozone? Well, if we're successful in reducing the NOx and VOC emissions, then we should see a reduction in the Northern Hemisphere ozone background, as well as in local ozone hotspots. But the reduction in NOx will reduce local titration of ozone, so we will see, at least temporarily, some increase in ozone in cities probably, as NOx concentrations reduce, but that does depend to some extent on what happens to the background ozone in the Northern Hemisphere and whether that declines very quickly. So ozone is quite a mixed picture, but if we get things right, we should see, I think, substantial improvements in ground level ozone. In terms of the 2021 WHO guidelines, I think most countries will find the 5 microgram per cubic meter guideline for PM2.5 extremely challenging, and in many countries it may actually be a level below what is a genuine natural background. But NO2 is much more tractable, and a guideline of 10 micrograms per cubic meter should be achievable in many countries as we move to battery electric vehicles, as long as we don't start burning fuels like hydrogen, which will lead to NOx, thermal NOx formation. So the medium to long-term prognosis is that we would expect improved air quality with respect to PM2.5 and NO2. Biomass burning will become more prominent without additional controls. Non-exhaust road traffic emissions require regulation if we're going to drive down PM2.5 concentrations. And certainly within Europe, there are plans being developed to regulate brake wear particles. Tyre wear is more difficult, but there is work going on in relation to that. Trends in secondary particulate pollutants are hard to predict because of possible non-linearities. And the impacts of net zero policies are currently uncertain. Most countries don't have a very clear roadmap of how they're going to achieve net zero. So not only do we not know what technologies will be introduced, we don't know accurately what the effects of those technologies will be very often. So many of them will be beneficial for air quality, but we are likely to get some unintended consequences. Now, I'd like to use the last 10 minutes or so of the talk to say something about our work on atmospheric nanoparticles, in other words, ultrafine particles. There are currently 2 main sources. So in London, for example, the dominant source is primary combustion generated particles, mostly in London from diesel vehicles, although they are reducing quite significantly. They're sensitive to the sulfur content of the fuel, and they came down very fast when that was reduced. And also diesel particle filters are removing the solid particle fraction, but probably not the liquid particle fraction there. And then the other main source is secondary regional nucleation, which in many countries actually is more important than the primary source. And in Southern Europe, for example, it is very important throughout the year, but especially in summer months. Now, electrification of the vehicle fleet and the use of low sulfur biofuels will reduce the combustion emissions. And I think those low sulfur biofuels may be particularly important for aviation, where we do see very large emissions of very small particles because of the huge high sulfur content of the currently used fuels. So we've asked the question of how will future air quality changes affect regional nucleation? And I'm going to use an example of Beijing because we've done a lot of work in Beijing and I believe we have quite a good understanding of nucleation processes there. But we do look at new particle formation from regional nucleation as a fundamental process in locations as diverse as Beijing on the left and the Antarctic Peninsula on the right. But there's a remarkable similarity of some of the fundamental processes in these hugely different atmospheric environments. So looking at the urban situation and present and future atmospheres, we look at the mechanisms by which new particle formation occurs. And at the top right there, we see a plot of particle sizes, and we see in the middle of the day a new mode of particles opening up in the dark red, starting at about probably the bottom of the scale there, somewhere around 2 nanometers, and moving up and growing to, say, 20 nanometers by the end of the day. So new particles form from gas phase molecules forming thermodynamically stable clusters. These particles grow to larger sizes at rates from 0.1 to 10 nanometers per hour. Sulfuric acid and amines are especially efficient at forming new particles, and low volatility oxygenated organic molecules formed from oxidation of VOCs typically drive particle growth. And this is shown diagrammatically on this slide, so that initially a cluster is formed less than half a nanometer in size from sulfuric acid, itself formed from SO2 oxidation reacting with amines, possibly with volatile organic compounds. HOMs means highly oxidized molecules, those can also participate. And once that critical cluster is formed, it will condense further sulfuric acid and oxidized organics. And as it transitions beyond about 1.5 nanometers, it's no longer a cluster, it's a new particle, and those will continue to grow. They'll take up water, they'll become cloud condensation nuclei from about 100 nanometers upwards, and then cloud droplets. So this is a very important process, and thought to account for somewhere around 50% of cloud condensation nuclei in the atmosphere as a whole, but creating huge numbers of new particles in locations like Beijing. So in Beijing, the haze is largely secondary, so it's largely made up of sulfates, nitrates, and secondary organic aerosol. And some of the recent work has shown that new particle formation actually makes a substantial contribution to the haze, because although the new particles, when they're formed, are incredibly small and don't contribute any significant mass, they do grow very effectively. And we see that in the graph, that they're growing to well over 100 nanometers there over a period of days. And in doing so, they build up condensed materials, which we see in the bottom part of the graph. We see a build-up of secondary organics, of ammonium, sulfate, nitrate, and in some environments, chlorides as well, to which the nanoparticles make a significant contribution as nuclei to condensed material. And so particle formation, this is just skip past it, the mathematics. What we do, J is the nucleation rate, so the rate of particle formation in terms of number of particles per cubic centimeter per second. There is a function of sulfuric acid concentrations, for at the top dimethylamine, at the bottom ammonia. So we simulate that process first. Then the particle growth process, which is very dependent on the volatility distribution of the oxidized organic molecules. For those of you familiar with the work that's come out of Carnegie Mellon University, is now being used very widely in terms of effective vapor pressures. The effective vapor pressures seen at the bottom there on a log scale are extremely important in influencing the molecules that will condense and lead to particle growth, because only the least volatile will initially condense and lead to those growth processes. And there we see growth rates on the bottom left and particle diameter on the x-axis, so growth rate on the y-axis, diameter on the left, and SA, which is the biggest contributor for the very smallest particles, is sulfuric acid, because that's highly involatile. And then the least volatile organic molecules contribute. And as the Kelvin effect becomes less and less important as the particles grow, so less and less involatile molecules, more and more volatile molecules will condense and also contribute to growth. Now, those particles will also get bigger by coagulation, and that's also part of our model, that we grow those particles by coagulating small particles with larger ones, and we see there an initial size distribution in blue, which changes to the red size distribution, so the very small particles disappear as they steadily grow through coagulation into much larger particles. And in order to predict the future, we have to have an estimate of emissions. And so fortunately for China, there is the dynamic projection of anthropogenic emissions in China. And so we have taken emissions from those projections, and we apply multiplication factors to the current day emissions in order to reproduce and predict emissions in the future. So we have three scenarios: what we call baseline, which is business as usual, current targets, and a net zero, a carbon neutral by 2060 scenario. And for particle number concentration, top left, nucleation rate according to time of day, top right, bottom left, particle growth rate, and bottom right, number of particles by time of day greater than 100 nanometers. For each of those scenarios, we make predictions. And the results of those predictions essentially appear in these graphs. So if we start with the graph on the top left, those are the nucleation rates, and these are relative changes from the 2020 baseline. So the black is the 2020 situation. The light blue is a business as usual in 2040 scenario, and the dark blue a business as usual in 2060. And then the light green and the dark green are current policies, and the reddish colors to the right, and you only see one of those in the top left graph, these are the carbon neutral goals for 2040 and 2060. So the dark red is the carbon neutral for 2060. So we see the nucleation rates in the carbon neutral 2060 situation are extremely low. The next one is growth rates. They're still appreciable. Moving across, growth rates of somewhat larger particles, and then the condensation sink, which is an important parameter in predicting the coagulation. And then if we go to the bottom row of graphs, on the left, we've got the particles greater than 10 nanometers, and we see that those decrease hugely in the future scenarios. And then particle number greater than 100 scenarios, much improved, sulfuric acid concentrations, and oxidized organic molecules. So if I just read what's on the left, J is the formation rate of 1.5 nanometer particles. That reduces hugely, largely because of the reductions in sulfur dioxide. Growth rate is quite stable, but small changes in the VOC concentrations are offset by reductions in the condensation sink, and the oxidized organic molecule concentration is fairly stable. And the particle number measures depend highly on the nucleation rate, and these drop drastically. If we look at mass loadings, so this is very significant for haze in Beijing. These are the contributions of nanoparticle formation to particle mass, seen on the right there. And we do see for the blue and the green scenarios, so the current policies and the carbon neutral goals, we see very substantial reductions in the mass concentrations contributed by new particle formation after 12 hours to PM2.5 concentrations. So again, it's the SO2 reduction that's had a huge benefit there. Just one uncertainty, and that is that the volatility of the oxidized organic molecules is very sensitive to NOx levels because they affect the atmospheric chemistry and they shorten some of the oxidation processes. And as we vary the NOx concentration, it varies the oxidized organic molecule volatility. And we see that that can actually work in an opposite direction. As we increase the, as we decrease the volatility of the OOM, we get higher mass loadings. So if we decrease the volatility, so we move from right to left, by keeping NOx there, we form less mass. So the reduction in NOx may actually, unfortunately, lead to increases in mass. So just to summarize, it's a simple script used to simulate a single day's new particle formation in Beijing. The input gas concentrations are scaled based on different scenarios in the model. The baseline scenario produces more particles as SO2 and amines increase dramatically, elevating particle formation rates. Current goals, so these are current policies, will reduce SO2, amines and VOCs a little, reducing NPF intensity and resultant particle loadings. And the near zero goals will reduce SO2 substantially and reduce the particle loadings due to new particle formation. So future emission scenarios will be very, very definitely beneficial through this mechanism as well as other mechanisms on the haze concentrations in Beijing. So acknowledgements to colleagues in Birmingham who've been involved in carrying out that research work, and the National Environment Research Council for funding it. And many thanks for your attention. I'll be happy to take questions if there are any.
Thank you, Professor Roy, for such an enthralling talk. Just a minute, I am seeing if there are any questions. Yes. There is a question from Lakshmi. She is asking what factors, that is meteorological and dynamical, favor the formation of NPF?
That is a very difficult question to answer. So it's a very good question. I can give you some answers in terms of the situation in Europe, because if you look at the back issues of Atmospheric Chemistry and Physics, you'll find I and colleagues published a paper where we analysed the data from all of the European measurement sites for new particle formation. There are quite a lot of sites running SMPS instruments from which we can infer new particle formation processes. And we attempted to quantify independently the impacts of the different factors. Now that's in itself not a particularly good thing to do because the variables are not independent of one another. So for example, if the relative humidity goes up at a site, it's probably because the temperature has gone down and vice versa. So the variables are not independent. but I think generally we saw an increase in nucleation with higher relative humidity. And in terms of the dynamics, there's certainly some evidence that vertical mixing can be an important contributor, probably by bringing the various constituents and mixing them more effectively. There is very little impact of horizontal wind speed, very little effect at all. And as you might expect, as a meteorological influence, there's a strong influence of solar radiation because that's driving the formation of sulfuric acid and oxidized organic molecules. So the big factor there is the solar radiation, and the other factors are relatively minor and not totally independent of the sunshine intensity in any case. So I hope that goes some way to answering the question.
Professor Harrison, there is another connecting question with this from Lakshmi. Can we predict the NPF in advance using supporting measurements?
Well, this is essentially what we're doing for Beijing. We're basing it in our understanding of the current day, but we are predicting the future. So yes, there are, and in fact, although we haven't published this, we've developed an artificial intelligence algorithm that will predict NPF based on past experience. So there's two approaches. The artificial intelligence approach really depends on staying within the current parameter space. So current levels of primary pollutants, current meteorology, and so on. And then you can use past experience with artificial intelligence to make a prediction. Or the work that we've done there, as I talked about for Beijing, is much more rooted in the fundamental principles of understanding the nucleation and growth processes. And through that, you can move outside of current parameter space, as we've done there, and make predictions for different atmospheric conditions. So yes, it's all perfectly possible, but it's pretty hard work.
Thanks, Professor Harrison. I hope, Lakshmi, you get your answer. Now, the next question is from our iLEAPS ECR representative from South Asia. He's Saurabh Sonwani, and he has 2 or 3 questions. The first question is the presence of particulate matter in atmosphere is beneficial or harmful? That is the first question. Professor Harrison, can I read all of them or one by one?
One by one's probably easier, but the first one's fairly easy to answer. The particulate matter is very harmful to health. It reduces visibility. It causes the soiling of buildings. It's very hard to see what benefits there are from particulate matter in the atmosphere, very few indeed. So I think as a net effect is highly negative, particulate matter. In terms of climate regulation, it's much more mixed as to how different kinds of particles operate, but basically we don't wish to encourage unnatural particles to be in the air. So yes, happy to take the second part.
Actually, he's asking this question because some of the researchers mentioned that some of the components of PM can reduce the atmospheric acidity. And some mentioned that it is responsible for so much of the health and climate related issues. So that's why he's asking that question.
Well, the main factor that reduces atmospheric acidity is gas phase ammonia. Now, some types of particles can reduce acidity. Basic mineral particles can neutralize atmospheric acidity. But from a policy perspective, rather than encouraging the presence of basic mineral particles, it'd be much better to stop producing the acidic particles in the first place. And policy has been quite effective at that, actually, in countries that have cleaned up their atmospheres. The particle acidity is reduced substantially, so that's the optimal policy option, to stop reducing the sulfur gases and the oxides of nitrogen that lead to particle acidity.
Okay. The second question is, there are different VOCs which plays a significant role in SOA formation and cloud formation. So can we regulate such processes of cloud formation by altering such process or mechanism so that we can check the air quality through wet deposition?
Well, at the moment, we don't have a very adequate understanding of secondary organic aerosol formation. There are certain pathways that are reasonably well understood, but in terms especially of the urban atmosphere, we don't know reliably what all the precursors are, and we don't know the pathways by which the secondary organics are formed. In terms of cloud formation, I would suspect that the organics are not a huge contributor to cloud condensation nuclei. They will no doubt contribute, but I don't think they're a particularly large contributor to cloud condensation nuclei. But we wouldn't seek to influence cloud formation by influencing the organic content of the atmosphere. So I don't know whether there's any other part to the question, but I hope that sort of answered the first part of it anyway.
I hope, Saurabh, you get your answer. Now the next question is from Xavier. Please explain again why reducing NOx is expected increasing PM mass concentration.
Okay, this was just peculiar to the mechanism of new particle formation as a way of ultimately creating mass. If NOx emissions are reduced, then the oxidation of organic compounds will lead to less formation of nitro compounds. And those nitro compounds, when they form, tend to terminate the chain of oxidation chemistry, and they lead to an aerosol which is more volatile, an organic aerosol which is more volatile than if you have less NOx there, when you generate a higher level of oxidation of the organics. So we do expect, well, in fact, we see this in Beijing, that there's a very high concentration of the oxidized nitro compounds because there are high NOx concentrations there. But as those reduce, so the volatility of the organics will tend to reduce also, and they are more able to condense and turn from vapor phase into particulate matter. And that's essentially the mechanism, through an effect on the volatility of the oxidized organic molecules.
Am I audible?
You are now. Yes, you froze for a while, but I hear you now.
Sorry, there is electricity problem here. The next question is from Ashish Soni. He is asking, could you please tell what are the basic criteria of WHO for setting 10 microgram per cubic meter as a permissible limit?
The 2021 WHO guidelines used a common method, a similar method for setting the guidelines for those pollutants where there was a good base of epidemiology. So in the case of both PM2.5 and nitrogen dioxide, they looked at the so-called chronic effect studies. So they looked at those studies which had investigated the effects of long-term exposure to PM2.5 or nitrogen dioxide on mortality. So more people die in highly polluted areas, and so you can relate through epidemiology the death rates to the pollutant exposures. So they looked and tabulated the studies that they considered reliable from the epidemiological literature, and then looked at the concentration ranges of pollutants which had been measured in those studies. And when they put all of the studies together that they considered reliable, they looked at the 5 percentile of concentrations from those studies when aggregated together. And they set the guideline as a recommendation at that 5 percentile concentration point. So they said there might be effects below that concentration, but we're less sure about them. We believe that by taking the 5 percentile of the concentration distributions of the studies that showed effects of pollutant on mortality, that they could have confidence that that was a concentration having a small level of effect. And so they set the guidelines at that 5 percentile of the aggregated concentration data. So I hope that's clear.
Thanks, Professor Harrison. I hope, Ashish, you get your answer. Now, the next question is from Dr. Anshu Gupta. She is asking, do microplastics in atmosphere also lead to nucleation, and how much they contribute in new particle formation?
I think most microplastics in the atmosphere are present as relatively large particles. So I don't think they contribute really to the nanoparticle loading of the atmosphere appreciably. And because they are present as particles, not gases, I don't think they contribute to new particle formation processes. I think what we're looking at for microplastics is mechanically generated pieces of plastic, which will be relatively large compared to the particles formed in new particle formation processes. So they're more like the non-exhaust particles from road traffic, although they don't necessarily come from road traffic, but they are likely to be abrasion particles and relatively coarse in size.
Thanks, Professor Harrison. I hope, Anshu, you get your answer. The next question is from Xavier. In some parts of Europe, we see very difficult abating particulate matter. close to WHO guidelines without abating ozone, what do you think?
I don't think that ozone is playing a major role in particulate matter formation. Most of Europe has a problem with secondary particles rather more than primary particles. So we do need to be concerned about the mechanisms by which the secondary particles form. There will be an influence of ozone, for example, in oxidizing biogenic VOCs, but without running a numerical model, I'm not sure how sensitive particulate matter concentrations are likely to be to ozone, but my suspicion is that they're probably not very sensitive. So I think they're two separate problems. We need to work on the abatement of ozone and the abatement of particulate matter, and the policy measures will have certain amount in common, such as the reduction of NOx emissions, but there will also be significant differences.
Thanks, Professor Harrison. Professor Harrison, there are 3 more questions from Lakshmi. Do you want to take it or?
Yeah, I can take those. Yes, yes. Okay. Lakshmi is obviously very interested.
Okay. How the apportionment of chemical components were obtained in real time as shown in your slide? That is her first question.
Okay. I think the data to which you're referring are the ones from Beijing, and those are data from an aerosol chemical speciation monitor, an ACSM, which is an instrument that will give a near real-time readout of concentrations of those species.
Okay, the next question is how the NPF at surface level is different from that in upper troposphere and lower stratosphere region.
Well, we don't know a lot about that because new particle formation is not that easy to research, and we don't have a lot of data from other than ground level. There's been some work done in Beijing on the meteorological tower that they have there, which is, I think, about 300 meters in altitude. And there's a limited amount of work being done with research aircraft. So it all depends on the composition of the air at the particular altitude. We certainly do see new particle formation at a wide range of altitudes, but it will depend very much on the concentrations of precursor molecules at those altitudes. So there are differences, and they will vary from place to place. If you've got strong updrafts from the surface, then you may see relatively similar processes at different altitudes. But if you've got very differing composition at different altitudes, then the processes will be very different.
And the last question is, are there any studies that quantify the radiative impact due to NPF?
Not that I'm aware of. Yes, there are, but only when the new particles become cloud condensation nuclei and affect cloud formation. There are quite a lot of studies that take into account new particle formation as a source of cloud condensation nuclei, and then look at radiative forcing as a result of the cloud albedo. But there are not studies that look at the new particles themselves and their impact, because they're likely to be very small. They're too small when they're formed to interact significantly with either visible or infrared radiation. So they don't, when they form, influence the radiation balance significantly. It's only when they've grown that they can influence the radiation balance both directly and especially indirectly through cloud condensation nuclei formation. So it's a good question, and one I can only answer partially because it's really only part of that work that's been done.